I will explain division 2 problem C, fill in the matrix. Actually, I will not solve this problem using programming language because the process of implementing it is, you can find it in my screencast. So during the screencast, I solved this problem. How can we solve this problem? If we remove the solving part, actually there are just two cases, and maybe even three cases. So there are three cases: m equals 1. The second case is m greater than n, I think. And the third case is n at least m, and m is at least 2. So these are three different cases, and they should be treated differently. Let's solve them all. First of all, m equals 1. In this case, the matrix is a single column, and actually you are forced to fill it with zeros. This will make the only max in these columns, because there is only one column, 1. And the max of all these 1 numbers is 0. So the answer will be just 0 and a column of zeros. So this is a really boring case. The next thing is m is greater than n. In this case, you can get n plus 1, I think. Let's do it. To get n plus 1, you need to get source of 0, 1, 2, 3, 4, etc. n. And if you get, not source, but maxes. If you get all these maxes, then the max of these numbers will be at least n plus 1. I will prove that it is possible, and then I will prove that you cannot make greater than n plus 1. So, it is clear that if you want to get n, you need all numbers from 0 to n minus 1. Let us write them as follows. After that, we need to make n minus 1. Let us write it like 0, 1, etc., n minus 2. And so on. We continue this diagonal pattern. And finally, we get here in this column, for example, in this column, we get only 0 and 1, and in this column, there is only 0. So, okay, but these columns are still not filled with some other numbers. What should we put there? Actually, if you look here, you see that these numbers are consecutive, and you can try and continue this pattern to the right. So you now write n plus 1, n plus 2, etc. And here you have m minus 1. Similarly, here you have n minus 2, so you try n minus 1, n plus 1, etc. And here you will get m minus 2, and here you will get m minus 1, and so on. So actually, the upper triangle of this square is filled with like small numbers from 0 to n minus 1. And the lower triangle is otherwise filled with maximum numbers. So like m minus 1, then m minus 2, etc. Okay, you can try this pattern, and actually it works. Why does it work? Let's look, for example, at some column, which we want to be max m. How does it look like? The top several elements, not m, because m is reserved, k, we want it to be k. The several top elements are k minus 1, k minus 2, etc. 0. So the only thing that we need from it is that there is no k actually in this column, because there are already 0 1, etc., k minus 1. So the only prerequisite for it to be not k, for it to be equal to k, is that there is no k, the absence of k in this column. So let's look down to the 0. After the 0, there are m minus 1, m minus 2, etc. Actually, I claim that there cannot be a number k. Why? Because if there is number k somewhere here, then there are just a lot of numbers here. So here you have already k numbers. If you have m minus 1, etc. k, you also have how many numbers? If you have a segment of numbers, yeah, from A to B, how do you calculate the number of numbers in this segment? You need to subtract from the maximum number the minimum number and add 1. This is the common rule. You add 1 because you do not add 1 in case of semi-closed intervals, but in this case we have closed intervals from both ends, so we need to add 1 to deal with it. So the length of this interval, of this segment, is m minus 1 minus k plus 1, which is m minus k. So already we have k plus m minus k, so at least m elements in this column. But actually the size of the column is n, because n is the number of rows. So you get that n is at least m. And this is contradiction with this inequality. Here we have that m is greater than n. And this is important in this case, that m is greater than n. So in this case, what you get is so since m is greater than n, you will not get k in this column, and actually the XORs as I have written. So you you indeed can make the XOR n plus 1, but why cannot you make it n plus 2? In order to make it n plus 2, you need numbers from 0 to n plus 1 in these XORs. And I claim that you cannot make the XOR n plus 1. Why cannot you make XOR n plus 1? This is because to get it n plus 1, in this column there should be all numbers from 0 to n. But there are just too many numbers from 0 to n. There are n plus 1 numbers in this segment, but the total height of the matrix is less than n plus 1. It is just n. So you cannot make this max, and the max n plus 2 is impossible. Sorry if I said XOR and max interchangeably. In this problem, I always mean max, not XOR. So, as it's usual in these problems, in such problems, I have proved that the answer is at least n plus 1 by providing an example, and that it is at most n plus 1 by proving that n plus 2 is impossible. So if we have these two inequalities, we just can conclude that the answer is n plus 1 simply. Great. So here we have n plus 1. And the final part is n at least m and m at least 2. How do we solve problem in this case? In this case, I claim that the answer is m. The answer is m. First of all, let's achieve this answer. To achieve it, it's this answer. Yeah, we have some matrix n times m. Here it is, n times m, where n is at least m. First of all, let's cut off several rows in such a way that this is m and this is m minus 1. Okay? After we get this, so we have n prime equals m minus 1. So n prime times m, let me rewrite it like this. And I will use this color. So this submatrix is under this case. Yeah, because here m is greater than n. So you can actually feel this part, and you can get the answer n plus 1, n prime plus 1, which is just m minus 1 plus 1, which equals m. So if there were no this part of matrix, you could just get m as the answer. But if there is this part, there is no problem, because you can just take any row from the upper part and duplicate it as many times as you want. This will not affect the answer at all. Actually, note that we used that m is at least 2, because if m is 1, then n prime would be 0. And if n prime would be 0, then we couldn't duplicate a row, because there would simply be no rows. And we cannot duplicate anything because there is nothing. So it is important that m is at least 2. So definitely you can get the answer m. And the question is why you cannot get the answer m plus 1. The question is why you cannot get the answer m plus 1. And I kind of forgot why it cannot. Let me think. So theoretically, first of all, we can simply prove that you cannot get m plus 2. This is because if you fill a matrix with n at least m, or just for any m and m, yeah, so all numbers in all entries are between 0 and m minus 1. So each XOR, each max in all columns is between 0 and m. And after that, you can make, you can get that the max of these numbers is at most m plus 1. Can we actually? Yeah, I think, yes. We get that max is at most m plus 1. But actually, we can even prove that max is at most m. See, there are actually just m numbers. It's not important which actually m numbers, but there are m numbers, because there are m columns. So since you have m columns, you have m numbers, and it is easy to see that max of any m numbers is at most m. Minimum excluded number cannot be greater than m if you have just m numbers. You definitely exclude something less than m plus 1. So you cannot get any better than m, and here I showed you how to get m. If you want the solution is out there in the screencast.